right, good afternoon. I think we're finally getting the hang of how all this works. So hopefully we'll be a little smoother than usual. I'm going to do something a little out of the ordinary. I'm working with Hoda on an augmented reality project, so I'm going to present with her. So if we're ready. Dr. Hoda Azari is the FHWA's Non-Destructive Evaluation Research Program Manager. She's a structural engineer by education, and her expertise is in the area of NDE and structural health monitoring. Dr. Azari has over 10 years of experience in NDE and SHM on highway infrastructure. She's done extensive research studies for condition assessment, damage detection damage detection of transportation infrastructure, and performed forensic investigation services to state DOTs. She's also the FHWA's technical point of contact for application of UASs and augmented reality and artificial intelligence in highway infrastructure. And I'm going to present with Dr. Hoda. I'm Kevin Gilson. I'm with WSP. We're doing research with FHWA on augmented reality, and this presentation is pretty much some of the results of that research.
Thank you, Kevin. Do we have a pointer?
Just right here, the little green button.
Okay. Okay, good afternoon, everyone. My name is Hoda Azari. As Kevin mentioned, I'm from Federal Highway Administration, and I manage the NDE research program at Turner Fairbank Highway Research Center. So the main challenge in construction management and field operation are lack of real-time and integrated information. And with advancing technologies like AR, it seems to be the right tool to fill this gap and to overcome this challenge. So for that reason, at Federal Highway Administration, we initiated a research project to evaluate the applicability, availability, and reliability of AR technologies for inspection, construction inspection, highway construction inspection, and training, quality assurance, training, and project management. The final report, the draft final report is ready. If you're interested in reviewing the report, I'm more than happy to share it with you for your comments, and you're welcome to comment on the draft report. The final report is a publication department, so it's being edited. We are going to offer a webinar, a public free webinar on this topic. So if you're interested in attending the webinar, no registration is needed. All you need is the link with the call-in information. So if you're interested, see me or see Kevin. We have this flyer here in the back of the room. Or if you can email me, I can send you the flyer, or Kevin can send you the flyer. The webinar will be like a 45-50 minutes webinar covering the entire study research study that we performed through Federal Highway Administration. So with that, I'm going to hand it over to Kevin, who did all the work, and will be a more suitable person to talk about the study.
All right, thank you. And if, we have a timer here, so I'll use that to watch my own time. I'll raise my hand when I have 2 minutes left. All right, so this is a little diagram. It's actually borrowed from a publication from the mid-90s, which describes what's called the reality-virtuality continuum, or basically a sliding scale from full reality to virtual reality. And there are a whole series of different types of mixed reality in between the two ends of that spectrum. The two technologies that we're hearing a lot about today are virtual reality, which is complete immersion, total immersion, no reality involved. Augmented reality sits somewhere more towards the reality side. And that's what's interesting to us, is that blend of reality and virtual reality. Virtual reality, as I said, is this complete immersion. The most common thing you've seen are the headsets, where you're presenting your two eyes a complete virtual scene. They require, sophisticated 3D modeling techniques, and typically they're performed or played back with a game system. This is just kind of a video showing somebody looking around, so you get a feeling for how it works. You move your head and the scene reacts instantaneously and presents a stereoscopic view based on how the user is moving their head. And that action of moving your head and having the view change is a very important aspect of perception. This is a project looking at a station for California High-Speed Rail in California, where we're trying to present that experience of what it's like to have a train go by the station at 110 miles per hour. So the characteristics of virtual reality, the interaction connects the viewer to the scene. That touch, that movement, any kind of tactile response really helps to add to your perception of the scene. They have the freedom to view the scene any way they want. It's immersive. You're in a fully rendered stereoscopic scene with a wide field of view. And most importantly, stereoscopic VR presents a very accurate sense of scale. We always say that if you haven't tried it, you don't really understand that, because that stereoscopic view presents a very realistic view of the scene. But this report was more about augmented reality and where is that going and how is that going to change this notion. Several people today have mentioned that disparity between the two and kind of characterized VR as more of a design or an immersive tool that really presents a new scene to the viewer. Whereas augmented reality is augmented reality. It gives you both what you're looking at and then some kind of information placed on top of it. Most AR systems include a set of components, sensory input of some kind, display device, maybe some haptic input, a tracking system, very important, computing device, media representation, and then some kind of data input or storage. The most important aspect of AR is the tracking method, because the success of AR depends on what your virtual scene is showing and how it relates to reality and how close it matches reality. We're still not to an absolute perfect tracking system in any of the technologies yet. So one of the solutions is what are called marker-based systems, where you start the virtual scene with a marker. You've seen the little camera or smartphone AR tools where you point at a target, and that sets the scene, and then the device tracks the scene after that. There's two basic categories for AR that we're seeing. You've seen a lot of these demonstrated: the handheld devices, tablets, smartphones, and then head-mounted displays, HMDs, which, again, present a virtual image to the viewer's eyes. There's some classic little AR tools for your smartphone. If you haven't played with some of these, they're kind of amazing. One is obviously Pokemon, that lets you chase a character over a reality view. The other is Google Translate. You can point your phone at a sign, and it will replace the sign with the English word for what the phone is looking at. So there you have a smart AR app. But there are a lot of vendors looking now at the construction uses for these AR devices, tablets in particular. Most of the major vendors are developing tools which run on tablets. Trimble in particular is looking at melding a survey or tracking device with a tablet to increase the accuracy of the presented scene. HMDs, they're coming and going faster than we can kind of keep track of them. During the course of this study, several devices have come and gone. The most common that we've seen out there commercially is the HoloLens, probably. So what I wanted to talk a little bit about were some of what types of information AR is good at displaying. So we kind of categorize the types of information and what could be displayed. Obviously, there's displaying what it doesn't exist yet, what hasn't been constructed. And that's very easy with AR because it's typically in front of what the existing scene is showing. There's displaying what's intended to be construction, a design or design alternatives. Checking quantities. We see a huge application in inspection for AR. Displaying what's hidden from view, this is more complicated. Perhaps you're trying to show embedded entities within a structural element or some element that's behind something in an existing view. Much more complicated because typically you have to do some kind of occlusion calculation to show what's behind something else in the scene. And then the other that kind of gets forgotten about is the idea of displaying abstract information, textual information, annotation, other types of information that could easily be overlaid on the existing scene and add to the intelligence of that scene. Kind of like the menu app that I showed earlier. Some of the tablet-based apps that we found out there when we did our research. Trimble, as I said, is doing some very interesting things. These were some images provided by them that show what the scene looks like in the tablet. On the left, you see an underground MEP utility, and on the right is a new roadway overlaid on an empty construction site. So you can see how this could be very useful. Most of as I said, the vendors have developed cloud-based systems that provide data to different types of tools. We've heard about BIM 360, Bentley has Connect. Trimble also has a cloud-based application for sharing data between devices called Trimble Connect. I think I was going to delete the slide, but it's a couple more images that Trimble provided. One showing a changed edge of roadway on the right, and another look at utilities underground with some annotated information associated with it. And again, these are all captures out of their device in the field. So then HMDs, much more variation in the types of devices that are available. You can't really read this chart on the right. It was in the report, and it just looked at several devices that are on the market. The most interesting fact in there is the field of view that's displayed by each of the devices. The technology is still in its infancy, and so there's a real limitation on field of view. The image on the left shows a device that a contractor or a designer was playing with, showing a bridge application, which I'll show a video demonstration of in a moment here. So this was a project that Condot for a project called the Q Bridge. It's the new bridge over the Quinnipiac River in New Haven. We had a 3D model of the project that was used for visualization, and Condot wanted to experiment with a HoloLens to see what they could do with that model and how they could display it in the device. So these are captures out of the HoloLens display. On the left is the classic sort of model on a table, which I think is going to be a very valuable thing for AR to be used for, to have several people looking at the same model on a table as though it was a physical model. But then with a couple of commands, you could scale the model up to whatever scale you want it to be, even up to full scale. So there's audio with this video, if you could turn it up just a little. This is that bridge application that I was talking about. It was developed by a bridge lighting group, and it shows different alternatives for lighting schemes on the bridge. And you're seeing the virtual model overlaid on what the gentleman in that previous photograph was looking at. And you can hear him saying the color. Color yellow. Orange and yellow. Color blue. So that's something very interesting with the Unity drivers for HoloLens, is it lets you create audio-driven commands so that you don't need to use your hands.
Turn pure lights off. Turn pure lights on.
But one challenge that they found in doing this project is they had to go out at dusk because of the illumination issues with some of these devices. If they're out in bright sun, they aren't necessarily very good at displaying easy to see information. So we also found there were some very interesting studies going on looking at using head-mounted devices to measure elements in the field. The devices are scanning what they're looking at constantly and creating 3D surfaces as they do that. So the lab in Los Alamos and the University of New Mexico did a project together where they looked at using the device to measure data in the field. And this was a little study that I thought was interesting. The gentleman stood in each of these 2-foot by 2-foot areas, some distance from a target, and he measured the target with the HoloLens. And then they captured those numbers, and they found that they were within 1% to 2% of the actual measurement each time, the 12-inch measurement. So the accuracy is pretty good. They felt that the inaccuracy was more based on just the movement of the head while they were trying to measure. So then they took it one step further in thinking of this idea of inspection. Could they use the device to go out and measure quantities or areas for work that was done in the field? What I wanted, they had a term for it, which I meant to write down, which I think was augmented quantification, which I thought was kind of interesting. What you're seeing here is the surface as captured by the head-mounted display on the left, and there are some points in there that you can kind of see. And on the right are the area measurements that they came back with. They measured each area 2 or 3 or 4 times and then compared the area with a survey of the actual work. And again, they found they were within 2% of the surveyed measurement, just using the HoloLens to measure points around the surface. So pretty exciting and interesting kind of reversal of AR, collecting information as opposed to taking information out to the field. Another study they did was a ramp slope study. So they measured several points on a sloping ramp to check for ADA compliance. And I just show this video because to me it's a great kind of marketing effort showing what could be with AR. This is done by ThyssenKrupp, the elevator company. And it's just kind of cool what the guy does with it. And theoretically, this is all possible with enough development time behind it. It may be too long for the time that we have, but he goes out and he sort of sees stuff behind the elevator. I'll just show this one that I thought was kind of fun. What it shows at the end, which if you search on ThyssenKrupp, you can find it, is that he actually sees a video of an expert back in the office and they're communicating through the HoloLens device, which I think, again, is theoretically possible if you have the right kind of communication bandwidth. And if you haven't seen that, that's the classic gestural command for a lot of these devices. So lastly, I just want to talk a little bit about challenges. I mentioned it before, field of view. With a handheld device, you're limited to whatever can be displayed on the tablet device. So you'll find yourself moving around quite a bit if you're in the real world. And this kind of explains that a little bit. Each eye roughly takes in about 135 degrees, and combined, we get typically 120 degrees of binocular vision. Most of these AR devices are 60 degrees or less. So you've got this thing floating in space in the middle of your view. And it can be very kind of disconcerting, or it ruins the suspension of disbelief. And you're moving your head around quite a bit with these things. Occlusion is another big issue, as I mentioned earlier. It's a very complicated 3D calculation to hide a 3D element behind an existing element, especially if you don't have a detailed 3D model of the existing condition. So you can imagine to have my hand be hidden behind something in that scene, it would have to understand the shape of my hand and be able to do a masking calculation on that. Ruggedness, durability, performance, portability. Most of these devices are meant to be tethered, untethered, so they have to have the onboard processing power, computer, memory, everything, a small computer system that's portable. Safety is a big issue. You're covering your eyes with a virtual device, or with this tablet, you're holding it out in front of you while you're walking around on a construction site. The tracking technologies, as I mentioned. Most importantly, what we found was the optical 3D sensors are not very good in bright light, and the tracking doesn't work very well on an empty scene. So if you're out at a construction site, which is a big dirt field, these devices are not going to work very well. So that's a real challenge that needs to be overcome. And because of that, I think we're seeing much more rapid motion in the tablet devices rather than the head-mounted displays. I mentioned that all the various vendors have cloud-based applications for sharing data. It's basically the BIM workflow. I think what we're going to see is that these AR devices are going to piggyback on BIM workflows. So as long as you have a mature BIM workflow, I envision these AR devices just being a plug-in to that workflow. These were the kind of, I reiterated a lot of, or mentioned a lot of these during the talk, but basically the hardware is changing very rapidly. We're going to see just big changes over the next few years. Some of these devices have come and gone during the course of our research. Highway construction is going to be a challenge. Tablet devices making advances much more rapidly. There are a lot of entertainment-focused applications for tablets. If you haven't seen the Apollo 11 thing, it's pretty cool. You can watch the whole moon landing in an AR presentation. And as I said, very similar to BIM workflows. So I think we'll see that as kind of the, once that's advanced a little further, these will become just another part of that workflow. So I went a little over, thank you. Nobody yelled at me to stop. Can I answer any questions? So as we said, there will be a webinar where we'll go through a lot of this, plus more, as well as the report, hopefully in a few months. So. Because you go to the mic, right? Yeah. Or I have a handheld here.
Hi. I was just wondering about the safety issues or concerns wearing a head-mounted display, losing peripheral vision. If you take that to the field, how has the crew reacted to that or their feedback on it?
Well, again, most of the devices out there are kind of research or marketing oriented. There isn't really a productive tool out there at this point, although many of them now have hard hats integral to the helmet. Several companies make hard hats that fit on the helmets. I'd like to, we did a series of workshops where we had people discuss what they thought were going to be opportunities and challenges with these devices, and that came up quite a bit. And one of the ideas that came up in the discussions is perhaps the device should be smart enough to help you be safe rather than hinder you. I mean, it should know what's going on around you, where the risks are, where the dangers are. It could warn you. So maybe that's what has to happen.
Also, have you looked into RealWear? It's another head-mounted display, but it's kind of like a band and has a minimum peripheral screen.
It's monocular, not rather.
Yeah.
Yeah. That particular one, I didn't, but we focused more on the stereo, just thinking that that was going to be a more robust platform, except for that abstract information like Google Glass is really good at just giving you textual information. All right. Thank you.